For this problem, we have the following configuration. It's a cantilevered beam with a wall on the left side and a load P, concentrated force, at the right end. And the question invites us to calculate the maximum deflection of the beam. And we're then, after we've done this calculation, going to solve the same problem using finite element analysis or the finite element method in FreeCAD. So for calculating the maximum deflection, we can use tables. And this table that we have here comes from Wikipedia. And if we go down quite a bit into the article, we can find that there are different conditions described. So simply supported beam with central load, simply supported beam with asymmetric load, and we see here that we have a cantilever beam with end load. Now, please be aware, and there's even this beware written on the slide, that there are different sign conventions in use in this particular article and in many of the tables that you might find on the internet. The bending moment diagram, for example, is flipped from what we would calculate in this class using the conventions from Hibbler's book. It would be down at minus PL instead of at positive PL at the wall. We've done this even in some of our examples previously. So that would go from here up to here. The shear force that we have, it seems to be drawn negative, but it would be up here and have a value of P. And the deflection curve or the elastic curve that we see here is correct, but we would say that this going downward would be in the minus y direction, and so that would have a negative PL cubed over 3EI for the maximum value of displacement, which is happening on the right side. So these are just a few things to keep in mind when using tables that you might find on the internet, but being able to solve these types of problems with information that doesn't look exactly like what you might have seen previously is an important skill to develop. So at this point, we have this equation PL cubed over 3EI. And yes, they're not using little v, they're using W or omega, depending on how you want to read that variable, for that displacement. So once we've taken this equation, the PL cubed over 3I, and we can put a minus sign in front of it because that would match kind of the convention that we've described for these elastic curves, we can go ahead and use parameters that might be given. We hadn't given any numerical values yet, but here they are. Length of 1 meter, width of 0.2 meters, height of 0.1 meters, so geometry parameters. And then load, 1,000 newtons, and material property being 70 gigapascals for aluminum. We can plug in the geometry to calculate the second moment of area, which is this value right here, and then plug these parameters into this equation. So we have, well, we're using all 6 of them. I, right, is dependent on the B and the H, the width and the height or the thickness of the beam. And we can calculate that the maximum displacement or the magnitude of maximum displacement would be 290 micrometers or 0.29 millimeters or minus that. And when we go further and we look at what the maximum bending stress is, we can use our flexure formula, the minus my over I, use that maximum magnitude of moment of being PL at the left side at the cantilevered wall, or at the wall, and we get a value of about 3 megapascals. So we've done a few calculations, and as we've discussed prior in the class, finite element analysis is often not used for just these simple calculations. I mean, it's great, but it is compared to these kind of baby step preliminary examples with analytical formulas like we have here before we go to the more complex geometries. We're not going to do more complex geometries right now, but this is just explaining kind of the way we think about things. Do the baby step first, make sure it agrees with the analytical expressions or the calculations that we can do in the class before you go to a more complex geometry. You'll find it's essentially a form of debugging. You'll find mistakes. So let's go ahead and bring up FreeCAD to do our finite element analysis, or perform the finite element method. We're using 0.21.2 and it's appearing on the welcome screen started on a different on my different monitor, but you can see it's 0.21.2. This might be a little bit different than what you're using. If you haven't already done so, it's probably a good idea to go to your preferences and click on display and use backlight color. Okay. I don't know exactly why it's programmed out like this, but for some of the finite element analysis, if we want to see the the colors in our results, like you can kind of see here, it's good to have that option selected. We're going to click Create New, and we're going to go ahead and come up here and first create our part. And don't use part design, we're just going to use part. And we're going to click this cube, and maybe we should recall what our dimensions are. 1 meter length, 0.2 millimeter width, 0.1 meter height. And we're going to be in millimeters, at least. That's what you'll see when you click on the cube. And we have length 1,000 millimeters. I just hit tab. Width 200 millimeters. Height 100 millimeters. Enter. And I'm using the Tinkercad option for the mouse just because that seems to be comfortable with a 3-button mouse. And there's our geometry. We'll then go ahead and enter the finite element method, and we see a new bit of icons up here. The first thing to do is click on the analysis container on the upper left, which then allows us to have more options available. And right now there's just this solver CCX tools in there. We come over here and we're gonna click on this sphere for creating or selecting material properties. And since we're doing 70 gigapascals for elastic modulus, aluminum generic is just fine. Note that if a finite element package doesn't have the exact material that you want, you can find the properties on the internet and then place them or edit the parameters in the material that you're selecting. Okay, so now we got our material solid. We can kind of move over from left to right, and we get to this one right here, which is for a constraint fixed, or fixed constraint. And we can rotate a little bit like this. We can click add, we can select it, and that is now going to be our fixed constraint. That's just the symbol that it uses. We hit OK, and we are now also needing to apply a load. So the load that we can apply here is considered a constraint, at least in this package. So we'll click right here, we'll click add, and then we'll click this face. And we notice that the load is not going in the right direction and is also not the magnitude. So the magnitude is supposed to be 1,000 newtons. And the direction, we will we'll click this line here, which is going to give us, whoops, okay, direction, select an edge. Yes, I was trying, there we go. Okay, I guess I had multiple things selected. So now that edge is selected, but we see that the force is going up. That's okay. I mean, it would be a symmetric problem and be allow us to, have a positive instead of a negative value. For the z direction, I don't know if you can see the axis, but the coordinate system, but the z is up, at least in the same direction as these arrows currently are. But let's go ahead and reverse the direction just so it looks a little bit more like what we've drawn or we have on that table. So now we hit OK, and we've applied our constraints. We've got our material. We need to create a mesh. So to do that, might be a little bit counterintuitive, but you click back on cube right here, and then these kind of voxelated options appear. We're going to go ahead and use the FEA mesh from Shape by NetGen. And here we have the option to select the maximum size of the element. I'm going to put in around, let's say, 30 millimeters. And the fineness, we can put in moderate. Okay, and then we'll hit apply. And we'll just take a look. You know, this is not bad. You might want to use more elements, a finer mesh. I'm going to use it like it is, though, so that it solves quickly. So we hit OK. And then we can click on the solver, and it actually will create another one. So we can, if we click on that one, or if we click on this one, we see that these other two yellow ones are open. So since it already has one in there, I'm going to go ahead and delete this solver CCX tool. I'll select it, and we'll click here, and this should run the solver. And now we wait. And there is a result. Okay, we see a table. So if we click over here or over here, okay, we should be able to come up with results. Now, sometimes this doesn't work super well. Okay, at least not out of the gate. So if we click here on the pipeline, double click, I mean, and we say, okay, we want to know a field. And let's just say we want to look at displacement. All right, so now we click on displacement, and we can kind of see, oh, there's color that now corresponds to the values that we see on the right. And magnitude is fine. We could also do in the z direction, okay? And if we do in the z direction, that means that this blue, and we'll hit OK here. So this is now looking at displacement. And we see there's kind of a little bit of maybe a slight amount of messiness. So there's different things we can do. We can kind of toggle visibility here. Okay, that didn't do it. Let's see. We might not be able to get much better than that. It's just a little bit of messiness here from the surfaces, but we can, I guess I'll take it. I'm not going to try to, I don't know if I toggle that visibility. Okay, that works. So you can see that it's kind of gotten rid of the mesh there. So what I did is I got rid of the mesh, or I toggled it so it was not visible. And so now we get colors, but then you don't see the mesh, right? So let's see if I toggle this visibility. Ah, that looks kind of good. CX results mesh. I like that. That looks like solid FEA. All right. So so now, remember, we were wanting to know the result, the maximum magnitude. Okay, in this case, since it's in the z direction, which is what we selected, right? We sorry, we had changed the field. All right, let's see. Yeah, double click there. All right, we had displacement in the z. We see that it's minus point, well, okay, it's minus 2.8 times 10 to the minus 4, and this is in units of meters, right? So that would be minus 0.28 millimeters, or it would be minus 282 microns. And if we look back at the value we calculated minus 288 minus 286. That's pretty good. So we're right in line. Okay, now this blue, right, you can see there are different shades of blue, so we don't know exactly what that value might be. But if we want to get close, we can do something that's also kind of interesting. We can go ahead and I'm going to click here, and then I'm going to, so click on CCX results, and we're going to, so we don't lose what we just did, we can create what's called another pipeline. So you come over here, okay, and now it's blank. This is a results pipeline. And we can go ahead and come down over here, or it may look a little bit different, and there's this thing that's called data at point clip filter. So we click that, and now what you can do is you can select a point, all right, and you can try to make it close to the node, but let's just put it kind of right here around the end. It's going to do interpolation, okay, and select that point, and we're going to select the field, and we can do displacement would be fine. So magnitude of displacement, like that. And look, we see that it's 2.82 times 10 to the minus 4 meters. So once again, that's just telling us what that displacement is at that location. If we want to know the stress at that location, which should be pretty close to 0, okay, we could go down and we can look at, say, the von Mises stress at that location, okay? And we see that it's 0.1 Pascal, or 0.1 megapascals, all right? Now you say, oh, that's a lot, but remember, that's actually a pretty small value, because it said 1.22 times 10 to the 5 pascals. That's a pretty small value compared to some of the other ones that we expect. So, for example, if we come back out here and we click on, so we can also double click this, right? And so let's go ahead and show the, well, let's see, we'll go ahead and do von Mises stress. That's fine. Okay, so here's the von Mises stress, and let's go back over here and let's toggle this visibility so we can see it, right? So we see that the stress is very low near the right end, and if we recall, this left end is the one that's attached to the cantilevered or the wall, and the one on the right is the free end. And if we recall that the bending moment is very low, okay, we go back over here, right? The bending moment is very low. Oops, that's the wrong one, but it's the same lower idea. The bending moment is close to 0, close at P, right? So that bending stress that we have is going to be very small. Now, we could have, right, there's a dmdx here, which is equal to the internal shear force, V. So you can have some transverse shear. And you can have some transverse shear stress, especially close to the neutral axis or the longitudinal axis. Okay, and so if we move up, so let's go back over here, and we click another, and double click here. If we click another point, okay, so this has got no field, and we'll just do the von Mises stress. If I move up a little bit, okay, I should expect that now, so that was at 0.2 megapascals. If I go up to here, all right, it went down. So now it's at 0.09 megapascals, right? Because I've moved away from the longitudinal axis, and I see that my stress value is different. For this problem, okay, for the homework, since it's asking for maximum displacement, you probably just want to go ahead and say, all right, let's do the displacement magnitude, or I could do displacement at one of these points, and either one, okay, is going to give you the 0.28 millimeters. So you could take a screenshot of this and include that. It might also be nice, All right, because that's just this screenshot. It might also be nice to include here in this pipeline, not the von Mises stress, because that's showing the bar here in a value, and instead go ahead and use displacement, right? And now we see that, yes, the displacement is going to be largish at this location, the 2.8, or the 2.8 times 10 to the minus 4 meters, and that's what you get along these points, along the edge. Another thing that you can do that is kind of fun is if you double click on the results here, you can have the software automatically calculate out some of these values. So if you want to say displacement in the z, for example, okay, it will show you the max and the min, and it can also show you a histogram. Okay, so a distribution of the displacement in the z. So here, what you see is that we have a minimum value for the displacement in all the elements of this simulation at minus 0.28 millimeters. Again, that is very close to the minus 286 microns or micrometers that we calculated analytically. The final thing that we haven't necessarily shown, and maybe it's not necessarily being asked in the assignment, is what is the maximum stress in this system? Well, we know that it's going to be by the wall. Okay, so there are a couple things we can do. Let's go ahead and look at the von Mises value. So it says that the maximum value is 3 megapascals. So that's very much in line with the 2.99 megapascals that we calculated, right? But maybe we don't exactly know where that is. So let's go ahead and do a couple things. We'll close this, and we'll come back to this pipeline, and we'll go ahead and we will double click here, and instead of displacement, we'll look at the von Mises stress. Okay, and we can see that it is higher, right, close to this wall, and there are Poisson effects occurring here. So there's constraint as you know the material is undergoing an axial stress. It's wanting to contract in the orthogonal directions because of the Poisson ratio, but the wall is not allowing it to do it. So another point that we've brought up in the past with finite element analysis is you have to be very careful with believing the values that the finite element analysis or finite element method will spit out near a constrained wall. So so here we can kind of see that there's some values around 3 megapascals that are relevant. With the von Mises stress, we can also, instead, if we want to use, say, a major principal stress, okay, so this is going to be like the sigma 1 value, we can see that, ooh, so these values, they get a little bit higher. They're at 4.5 megapascals, okay, so remember, there's Poisson effects happening here as well, so that can lead to some issues. And or we can look at the stress in the x direction. So we have a stress xx right there, okay, and it's a little bit higher, so it's around 4 megapascals, and it's the stress xx is nice because so that's the sigma x value. We can see that it's positive up here, it's red, and then it goes negative on the bottom, right? And that's ooh. Okay, let me see. There we go. And let's see, we can see that. And we expect that, right? We expect that the top is going to be in tension with a positive stress, and we expect that the bottom is going to be negative with a compressive stress. So if we want, we can clear these data points. We'll go ahead and delete them. Actually, okay, I'm surprised they did not delete. I guess they just got selected there. To be honest, I'm not quite sure how to remove them. But let's go ahead and we will go back over here and select some data points, and we'll do our field, which we'll call the stress XX component. And we can go ahead and, so that's saying at 0, 0, 0, okay? That's somewhere over here, but I'm gonna go ahead and specify my selection. I'll just do it a little bit off right there. And I get, again, something around 3 megapascals. That's 3.39 megapascals. Okay, so I hope that, and I'm not quite sure what the scale bar did. Let's double click here. Okay, I don't know exactly what it did there. That was interesting. Okay, but this, and some of the graphics are, you know, it's open source and it's a lot of hard work being done here, and maybe it's a little bit of my not knowing exactly how things are working, but this is a nice description. I like to have the mesh there often for people to see. Okay, now it looks like what we expect. Again, not always certain what it did. It did that weird like red and blue thing. But this would be a nice screenshot as well if you wanted to look at the stress and the x direction, the sigma x. And I like having just the grid of the finite element there, because at least when it's not super dense, so that you can see, okay, how fine was the mesh? Does it need to be refined? Are there any issues with the mesh itself? And how likely are you to have converged on an appropriate solution? Things that we will talk about in multiphysics. Well, that might be a little bit of a long-winded answer, but I'm grateful that you've spent some time working on this problem with me. Thank you.